going to do something a little bit different today. We're driving a late model JK with an LS3 6L80. We've done this combination many times before. This Jeep does have our CAN modules. It seems like a lot of you guys are gearheads and are interested in the ongoings of these conversions and engine performance. I was a level 2 or G2 emissions inspector for about 20 years. What that means is I was not only an inspector but a diagnostic technician. So we had to figure out how things worked. Not just inspect it and verify that it worked, but how did it work? Why did it work? Why did it fail? The G2 does earn his living. If you look at all the education they have to go through and the diagnostic theory to determine what's wrong with a vehicle, and you have to understand not only electronic theory but the mechanics behind it. Working out in the field for about 30 years, I've learned failures based off of experience. You see the same failures over and over, but every once in a while you get a weird one. It does involve more than just hooking up a power probe or a Tesla. You have to think from a theoretical standpoint why and what is happening. So let's start this off with one of the most troublesome areas, not only an engine swap, but just in general engine performance, and that's throttle actuator control or electronic throttles. Many moons ago, when I was roaming the earth with my hot rods, we had carburetors with cables that opened up butterfly valves or throttle valves. Sure, fuel injection was around, but it wasn't very much in use. The first fuel injection system I ever worked on was, well, actually it was the old Rochester Corvettes, but in a modern production vehicle it would have been the 1976 Cadillac Seville. It had a pretty primitive Bosch fuel injection system. However, it did have closed loop feedback O2 sensor. So for 1976, that was very advanced. We were still running a cable throttle body. If we fast forward a couple of decades, eventually most of the manufacturers went to electronic throttles, and there's a lot of reasons for that. Electronic throttles disconnect your foot from the throttle valve. And why do you want to do that? Probably the biggest reason is when you give an engine throttle, what you're doing is you're opening up blades that are allowing airflow into the engine. Under certain conditions, you can open those blades up too much, and by doing that, you make the engine less efficient. The engine can only put out so much torque, so much power, and bring in so much air. You've probably noticed, if you've driven the old carburetors, that if you floor it, you might start getting into a bog zone, and then if you let off, it starts pulling again. It's because you're letting too much air, or primary air, into the intake. Throttle bodies can control that much better than your foot. They know how much throttle or airflow the engine can take. So they can maximize torque, minimize emissions and fuel use by only opening up the air valve as much as is required or as needed by the engine. So throttle bodies became very popular in the 1990s. Then of course by the 2000s, pretty much everything has a throttle body. Throttle bodies make cruise control work much better. Throttle body do AC idle bump, so you no longer have to have a mechanical motor that bumps the throttle up or an IAC, that's an idle air control valve. So the throttle bodies solved a lot of problems, but they also created a lot of problems. Problem with electronic throttle bodies, and we're going to talk about throttle actuator control, TAC, and I call it that because that's what GM calls it. Early on there was a fear that if we took that connection between you and the throttle body away, that could somehow be dangerous, and it could be. All of us have heard by fly-by-wire airplanes, and they had similar issues. So we have to make the throttle body safe, and how do we do that? Well, we monitor it, and we have redundant systems and failure modes. And this is not just in the software, but also in the hardware, the wiring, and the sensors involved, and we're going to talk about those. Many of you might remember the sudden acceleration in the Audis way back, and then the Toyotas. The APP is the accelerator pedal position sensor. That's what it's called today. It's no longer a gas pedal. Whatever the reason, you don't want the throttle body to accelerate out of control. So manufacturers came up with what they call failure modes. Failure modes related to throttle actuator control are usually called reduced power modes. And reduced power modes can be a big problem, and not only in LSs, LTs, but even in your Jeep operating system, and pretty much every other manufacturer out there has problems with reduced power because it's a balance between keeping you safe and reliability. You don't want to be going into reduced power. We can start the discussion with the Generation 3 LS motors, I think. The Generation 3 LS motors, and you have to have a fundamental understanding of how GM designed, and this does not apply to every manufacturer because every manufacturer implements throttle actuator control differently. General Motors in the Generation 3 LS engines implemented throttle actuator control using a separate module. It was called the TAC module. This TAC module was mounted independent of the engine control module, or in the case of the Gen 3 motors, the powertrain control module. An engine control module controls just the engine, while a powertrain control module can control multiple components. So in the Gen 3 motors, it controlled both the engine and the transmission. The powertrain control module did not contain the TAC or the throttle actuator control internally. It used an external throttle actuator control. Not all Generation 3 engines had TAC. A lot of Generation 3 engines had cables. So you somewhat have a choice whether you want to run TAC or not in your Generation 3 engine. A lot of guys are still old school and want to run a cable. Now, we all know that engines are most efficient at wide open throttle, but there's a lot of inhibitors to that, and that's really a different discussion. These TAC modules could be troublesome. They were enclosed in plastic housings that were not really waterproof. They mounted them usually on the firewall of the vehicle, so they were exposed to heat and water, and what you'd end up getting was what's called reduced power. Reduced power is something that's not very well understood, but it can be somewhat of a concerning event. And there's several levels of reduced power. Depending on what the failure is, will determine how much reduced power you're going to experience. Reduced power can be a slight loss of power, or it can result in an engine shutdown. Most reduced power events, in my experience, are anything from a dead pedal, which means you basically go to an idle, to giving you a certain amount of throttle so that you can go about 40 miles an hour. So that way, if you're on the highway and you get thrown into a reduced power event, you can at least accelerate to the point to get off the highway. Now, what is it monitoring? Well, we're going to talk about that, but essentially the duration of the event, meaning how long the failure lasts, and the amplitude of the event, how far off are you from where it should be, will determine the level of the reduced power event. Now, Jeeps have a reduced power mode, of course. The little lightning bolt on your dash of your Wrangler is the failure light, or the telltale for the electronic throttle control. Jeep, I believe, calls it ETC, electronic throttle control. GM calls it TAC, throttle actuator control. It's all the same thing, really. So when that little lightning bolt goes off, a lot of you guys have experienced reduced power, and you want to know why. And it's not so easy to determine why, and that's why I'm doing this video. Even dealerships cannot properly diagnose, or should I say efficiently diagnose, reduced power events. I've experienced reduced power events for many years, not only in GM engines, but as a general mechanic. Crazy things can affect and put you into reduced power. Things that you would never expect could put you into reduced power. ABS modules and temperature-related codes can put you into reduced power. In fact, if you hit 265 degrees on an LS operating system, that'll put you into reduced power mode. It's called the hot protection mode. Basically, it's pulling the power back from the engine. It's adding extra fuel to try to keep the cylinders cool. So that's a reduced power event that you're inflicting through engine coolant temp. But I don't want to talk too much about that. I want to talk about how to diagnose reduced power events on an engine conversion. And a lot of this does apply not only to the LS, but also to Hemi swaps. And even if you're doing a supercharger add-on, or if you just have a stock Wrangler and you have a 3.6 or a 3.8, a lot of the information I'm going to talk about is going to apply. Obviously, we have to have electric motors that open and close the throttle valve. The assembly is called the throttle body. On that throttle body are throttle position sensor, or TPS sensors, and I'm sure most of you have heard of that. In the old days, we only had one throttle position sensor on cable-driven vehicles because, again, we had that mechanical linkage. There was no fly-by-wire, so there wasn't any redundancy in the throttle position sensor signals. On the other end, you got your foot. You have the accelerator pedal position sensor, or the APP. The APP also has sensors to determine what position the pedal is at, which is basically your demand for power. In the middle, you have the engine control module, or in this case, the throttle actuator control module. Now, the TAC module in the Gen 4 and the Gen 5 engines is no longer external to the ECM. It is actually built into the ECM. It is a separate module. It's a separate processor that they put inside of the engine control module. Gen 4 and Gen 5 engine control modules only do one thing, and that is control the engine. Things are so complex right now. Transmissions have their own modules. They're called transmission control modules, or TCMs. So by putting the throttle actuator control module inside of the engine control module, it is now isolated from the elements. It's no longer exposed to water. It is exposed to heat because these engine control modules are mostly put into the engine compartment, but with modern electronics, that's not a problem. In the early Gen 4 engines, GM had excessive reduced power events, and what they came down to was basically bad grounds, or not proper grounds. We have to talk about the battery, power distribution, and ground distribution before we can really talk about proper reduced power events and throttle actuator control. The battery is obviously the component that stores energy. Most of us know that electrons flow through currents. Electrons flow from the negative side of the battery into the positive side of the battery, and they go through the load device. The load device would be whatever you are powering, let's say a throttle actuator control or a throttle body. If you take a standard DC motor and you apply power one way, it's going to spin one way. If you apply power the other way, it's going to spin the other way. We used to have idle air control motors and idle control motors, and they were little electric motors. Cadillac was big on them, and basically if you put power in one way, it would cause the valve to open up one way. If you put power in the other way, it would cause the valve to move the other way. So you can control your idle speed by driving this idle air control motor or the idle speed motor. Some of them, they were ISMs. You could drive it both ways and the idle would go up and down. And that was a pretty crude but effective way of controlling the idle speed based on engine temperature. Remember, we wanted the idle speed to be higher when the engine's cold, or if you turned on the air conditioning, that loaded the motor down, you wanted the idle to go up. So you just apply power to this motor. It would move the idle air control motor plunger in or out. That would cause air to bypass into the throttle body and raise the idle, or it physically move the throttle valve to increase the airflow. In order for all these load devices to operate properly and for sensors to sense properly, they need proper ground and proper power. And there's different kinds of grounds. There's not just chassis ground. There's not just battery ground, and we'll talk about that in a minute. As far as the power goes, we all know that we got to have a good connection, a good circuit. If we have an open circuit or a high resistance circuit, whatever the device is isn't going to work properly. So if we start at the battery is a critical component. And unfortunately, a lot of these modern electronics do not like certain types of batteries. A lot of you like to run AGM batteries because they're sealed. Modern electronics need good, stable power and ground distribution. Unfortunately, some of the AGM batteries just don't have that. And I don't want to get too far into it, but let's just say that we've solved a lot of issues by replacing AGM batteries. And there are different levels of AGM batteries. Some are better than others. So power and ground separation is critical. Get a good battery. Don't get a cheap battery. Hand in hand with good power and ground separation is power and ground distribution. And we've talked about this many times in the videos before. The way a wiring harness lays out determines how well your power and ground distribution is going to work. You have to have multiple paths for ground distribution. If you gang all of your ground distribution into one wire, you're putting all of your eggs in one basket. Not only that, you end up getting what's called a voltage drop, and we'll talk about that a little bit later. So the manufacturers have determined how to get proper ground distribution with a minimal amount of wires. In the early days, they actually went too minimal. GM actually added ground wires to their early Gen 4 engines when they were experiencing a reduced power event. We all want to run the minimum amount of conductors. Conductors are basically wires. We want to run the minimum amount of wires and the smallest gauge that we can. It makes the wiring harness clean, it's cheaper, etc. But we also have to get that energy or that current to the device. So an electronic device like a throttle body is probably going to use more current than a sensor, because the sensor really doesn't have many moving parts, if any, while the throttle body is physically moving an electric motor. It's moving a valve, so it's going to need more current. So you have to size the wire properly. And it's not only the load the device uses, but how far away is it? If you have a sensor that's 12 feet away in the back of the vehicle, that sensor may have a different wire requirement than a sensor that's only a foot away from the ECM. So all this comes into account, and the manufacturers spend a lot of time and money engineering and developing these harnesses so every sensor and every load device gets the power and ground that they need. Here's something that's critical: low reference. A lot of guys don't understand what low reference is. Back in the day, let's talk about the 70s and 80s when oxygen sensors became popular. Oxygen sensors actually have been out for a long time, but we didn't see a lot of them get put in until the 1980s. We actually used closed-loop feedback carburetors in the 1980s with oxygen sensors. Oxygen sensors were pretty primitive back then. Oxygen sensors essentially sense how much oxygen is in the exhaust system, which at stoichiometric is about 1.5% oxygen. That's after combustion, we have 1.5% oxygen left. The narrowband oxygen sensor can only sense stoichiometric, which is 450 millivolts, which is now stoichiometric. So it would target that voltage and switch above and below it. Above 0.45 volts, you're rich, and below that, you're lean. So it would give a lean command, rich command, lean command, rich command. That's why you see your oxygen sensor switching. Well, the early oxygen sensors, while they worked well, they had to get hot. The oxygen sensor would come online once it reached a certain temperature, then efficiently become a voltage generator and put the small amount of voltage out required by the ECM to determine what the fuel mixture was, or at least what stoichiometric is. Early oxygen sensors used case ground or chassis ground, which made them very inaccurate. Now, would they switch? Yes, of course they would. Using chassis ground is not very accurate, and the reason is you have what's called voltage drops. Depending on how much resistance this ground has to go through. Remember, we're going from a battery, let's say, into a frame, and then from the frame into the body, and then from the body over to the O2, whatever. We have losses, meaning we don't have 100% continuity between the device and the battery, or the device and the computer, which is even more critical. So we have voltage drops, and you can check voltage drops or voltage differential by putting your meter into a sensitive mode, let's say 0.2 of a volt or a half a volt scale, and then measuring along that circuit. If you're doing a voltage drop while starting the engine across the main ground cable, you might see a 1 volt drop, but we're also pulling 250 amps, so that 1 volt drop isn't that much. But if you look at an O2 sensor, we don't want to see that drop. We're only pulling milliamps, so we want to see just millivolts on your voltage drop. If you're seeing more than that, then you got a problem. So the manufacturer said, okay, we can't use chassis ground to get accurate sensor feedback. What can we do to make this sensor feedback more stable and more accurate? They came up with what's called low reference. And what low reference is they ground the engine control module. They use a traditional ground. If you look on most computers, they have a large ground wire that grounds that module. Then the module puts out ground to these sensors. The module puts out what's called low reference. Low reference is ground supplied by the module. By doing this, the module now has an internal reference what ground is. Meaning, if we were grounding an O2 sensor off the battery versus grounding the O2 sensor off the ECM, it's going to be much more accurate to ground it off the ECM, because the ECM knows what the voltage drop or the voltage differential is between itself and the battery. That way, the sensor output or feedback into the ECM is much more accurate, much more precision. Most sensors have a low reference. Some sensors that aren't critical don't have low reference. They can still use chassis ground. But if you look at an oxygen sensor, a MAP sensor, most of those run off of a low reference. MAF sensors still use chassis ground because that is a digital signal. So really it doesn't have an analog feedback into the ECM. It's using a frequency. And a frequency controlled device does not need the accuracy of having low reference, because really all it's doing is switching, and the computer is looking at the frequency or the hertz rather than look at the analog feedback from that sensor. So different sensors may or may not require low reference. Now, it's critical to understand low reference because when you're testing that device, you have to understand that the ECM is now supplying the ground. This is why ground distribution is so important in an engine harness. The ECM being properly grounded will supply a low reference to these sensors. Of course, the ECM provides low reference to both the throttle body and to the accelerator pedal position sensor, and it does that because it needs accurate feedback. Both the throttle body and the accelerator pedal position sensor run 0 to 5 volts on these GM LS and LT motors. Here's the part I want technicians to listen to carefully. In both the throttle body and in the accelerator pedal position sensor, you have redundant sensors. Why do we run two sensors? Obviously, they are redundant, and we're going to concentrate in the throttle body right now. The accelerator pedal does work in a similar fashion, but we're just going to cover the throttle body. So, at the throttle body, we obviously have 3-wire sensors. And that basically means we have power, we have ground, or in this case low reference, and then the signal returned back to the computer. The computer is going to supply a 5-volt reference. Why a 5-volt reference? Well, we want these sensors to work all of the time. Back in the day, sensors would work off of 12 volts. The problem with that is if your system voltage went below 12 volts, like you're cranking, the battery's going bad, the alternator quit, the sensor would stop working. So they went to 8-volt sensors. Chrysler used 8-volt sensors for a while, and that was determined not to be low enough. So basically all the sensors went to 5-volt. There's some 3-volt sensors out there, but 5-volt's pretty much the industry standard right now. That way, even if you're cranking on a low battery, you're probably not going to drop below 8 or 9 volts. The sensor's still going to work. We have 2 signal feedback. We have throttle position sensor 1, or TPS1, and we have throttle position sensor 2, TPS2 signal. These 2 signals are critical. This is what the vehicle uses to determine where the throttle body is at. How much throttle you are demanding will determine how open this throttle body is. And it's critical the computer determine this with a high degree of precision, because if it determines that that throttle body has a failure, then you're going to go into reduced power. The computer now is going to get, and this is actually the throttle actuator control module, is going to get these 2 signal feedbacks from the throttle body, which is great. You have 2 sensors. Both of these sensors are 0 to 5 volts. However, one sensor operates 0 to 5 volts, the other sensor operates 5 to 0 volts. The reason they work in opposite directions is the end result is a percentage. If the throttle body is open 5%, 10%, 20%, both of these sensors must be in agreement. There's what's called synchronization, and if they go out of synchronization, then you're going to go into reduced power. So if you were to look at throttle position sensor 1, throttle position sensor 2 data, and they both need to be exactly the same, 19%, 18%, 17%, and they need to follow exactly. If you see those percentages move, let's say one says 20% and the other one says 22%, we got a problem. The level of reduced power will be based on how much this error is and how long the duration of the event is. So if you go 2% out for 10 seconds, the likelihood is you're going to go into a reduced power event. If you go 2% out for a millisecond, the likelihood is you're not going to go into reduced power. If you go 20% out for a half a second, you're going to go into reduced power. So again, the amplitude and the duration is going to determine the reduced power event. Let's get to the important part of this. The throttle body has 2 sensor feedbacks, and the voltages are 0 to 5 and 5 to 0 volts. What that means is these sensors are actually running opposite directions as far as the voltage goes. The reason they do that is we're only supplying 1 low reference to this throttle body. That means we only have 1 ground signal to this throttle body. So if we start losing ground, or if we start losing low reference, which is the computer's ability to supply ground to that sensor, then these signals are going to separate. If these sensors operated in the same direction, then both of them would err in the same direction and you would not see that differential. So by making the sensors work in opposite directions and grounding them off of the same low reference, when a failure does start to happen, let's say the ground wire going to your ECM gets weak, that will cause a weak low reference, which will cause the signals to separate and you go into reduced power. If you have a reduced power event, what you want to do is capture the freeze frame data. By capturing the freeze frame data, you can go in and see what sensor read off from the others. So you might see that one sensor is at 17% and another sensor is at 65%. Obviously, one of these sensors was wrong, and it will throw a code usually pointing you to what happened, meaning the TAC module is capable of its own diagnostics so that it can determine it was a low reference problem, it was a power problem, shorted to ground, a circuit failure. And by looking at that circuit failure code and then combining that with the freeze frame data, you can pretty much narrow down exactly what the problem is. If a sensor fails, pretty easy to figure out. If the problem is intermittent and it only happens when it's raining or when it's cold out, it's wet, it's icy, the electrical system can have more problems. So the hard part is determining if the problem is not a component. If the problem's in the wiring or in connectors, now we've got to be Sherlock Holmes. We've got to figure out where this problem is. So the first thing I would suspect would be any connectors between the pedal on your computer or the throttle body in your computer. The throttle body connector is extremely sensitive. They're usually gold plated. So you want to look at that throttle body connector very carefully. You want to tug on the wires. You want to check the integrity of that connector, because that connector goes directly to the ECM. Now if you go right back to the ECM, you pull that connector off, do the same thing. Inspect the wires and the terminals in the ECM and the ECM connector carefully. Take it apart if you have to. If you see any pins bent, broken, corroded, fix it. Jeep had a problem in some of the early harnesses where sensors were being pulled on because the wires were too short, like the cam sensors, and that would actually throw you into reduced power, light the lightning bolt up. By approaching it logically and understanding the theory behind what is causing you to go into reduced power, throttle actuator control modules do fail inside of the ECMs. A lot of times you'll throw a 500 code, like a 516 or a 1516, something like that. Internal processor fault. That could be an indication that your module is going bad. Now, in most cases, just by clearing the codes, you'll get your power back. You can even do this on the road if you have to in an emergency situation. But do one thing at a time. Don't shotgun it and replace the pedal, the throttle body. You're never going to know what fixed it. So, do it intelligently. If you have a reduced power event and you have the time available to you, stop, pull freeze frame data. Most scanners now, good scanners, are capable of pulling freeze frame data. See what the code is, play back the freeze frame data, see which sensor went out of range, then narrow in on that sensor or that circuit. Hopefully this video can be some help to guys out there trying to diagnose issues with their throttle actuator control or electronic throttle control.